All right, in this Big Ideas Algebra 2 tutorial, we're going to begin Chapter 4 and look at how to graph polynomial functions. So one of the major things is to be able to identify what makes a polynomial function different than a quadratic or a linear, what we've talked about previously, and then how to graph those using both tables and end behavior. So a polynomial function is something that consists of multiple or even just one monomial. And remember, a monomial is a number, a variable, or the product of a number and a variable with whole number exponents. So you're not allowed to have fractions in your exponents. A polynomial just means that you could be adding multiple of these monomials together. And the chart down below looks at the different types of polynomial functions depending on what the highest exponent that you see is. So if you see a polynomial function with a degree of 0 or an x term that is raised to the 0 power, which means it does not have an x term, that is a constant, just a number by itself. So for example, f of x or even y equals -14. Linear is something that has an x with an exponent of 1, so 5x minus 7. There is an invisible exponent of 1 above that x. Quadratic is what we focused on in the last section, and that is anything with the highest exponent of 2. Cubic is anything with an exponent of 3, and quartic is anything with an exponent of 4. So let's first decide on whether each one of these functions is a polynomial or if it is not. If it is, then we'll need to write it in standard form so that its highest degree is first, then label its type and leading coefficient. So for part A, we're looking at -2x to the third plus 5x plus 8. This function is a polynomial and it is already written in standard form. It has a degree of 3, which is a cubic function, and its leading coefficient is -2. Part B, -0.8x to the third plus square root of 2x to the fourth minus 12. This is a polynomial function, and written in standard form, you're going to rearrange your exponents so that the highest exponent is first. Square root of 2x to the fourth minus 0.8x to the third minus 12 is its new standard form. It is a fourth degree or a quartic function, and its leading coefficient is the square root of 2. Part C, this is not a polynomial function because the term of 7x to the -1 has an exponent that is not a positive whole number. -1 makes this a rational function, and that is something that we may talk about later. Part D is also not a polynomial function because 3 to the x power, you must have whole numbers in your exponents, so x as an exponent does not work. All right, end behavior is one of the main objectives of this section. It is what you notice about the polynomial function as the graph either approaches positive or negative infinity. So as the graph keeps moving to the right, does it go up or down? And as the graph moves to the left, does that go up or down? So depending on what your degree is and what the leading coefficient is, will dictate what your end behaviors are. So if your highest degree is an odd number, so 1, 3, 5, or 7, and the leading coefficient is a positive number, as x approaches the left, it will go down to -infinity, and as x approaches to the right, it will go up to -infinity. So notice those arrows dictate what the end behavior is based on your degree and leading coefficient. So if your degree is still odd, but now the leading coefficient is negative, it is basically just flipped. So instead of to the left going down, it is now going up. And then instead of to the right going up, it is now going down. So that negative or the positive in the leading coefficient changes. If your degree is even, both of your end behaviors are going to be the same. So think about in the last unit when we had quadratic, that is an exponent of 2. Both of your end behaviors were the same. They would either both go up or they would both go down, again, depending on what your leading coefficient is. If you had a positive a back in our quadratic section, it would be pointing up. And if you had a negative a, it would both be pointing down. So that end behavior still stays the same as you approach degrees 4, degrees 6, or even degrees 8, the higher up you go. So let's describe the end behavior of this function, negative 0.5 x to the fourth plus 2.5 x squared plus x minus 1. So this is a degree 4, which is an even number, and its leading coefficient is negative. So because your degree is even, your end behaviors are going to be the same direction. And since it is negative, they are going to both be pointing down. So as the graph moves to the left, it will be pointing down. And as the graph moves to the right, it will also be pointing down because your leading coefficient is negative. So looking at now how to incorporate that end behavior into a table with some of these polynomial functions, looking at some corresponding points and then connecting that curve to check the end behavior. So again, choose some easy points, use 0, 1, and 2 as your checks for this table. So as you are plugging in along with, I don't know why this table formatted did not come in, but you have a -2 first and then a -1. So when you plug in -2 into this function, you get a +3. When you plug in a -1, I don't know why these numbers are not popping up, but those are what the coordinate points you should be getting as you're evaluating for your -2, -1, 0, 1, and 2. Again, this is just plugging into your x value, and you're going to get your -4 here, your -3 here, and then your -1 here in this spot. So you would then connect those dots into a smooth curve, double check that your end behavior matches. So since this degree is an odd and your leading coefficient is negative, you are going up to the left and down to the right. So that matches that chart we had gone over previously. Part B, again, we're looking at this table. You have your -2 and your -1 that are not being imported, and then your y values that are 12, 1, 0, and 2 into that function. Again, connect those dots together. Double check that your end behavior matches. So you have a degree of 4, and then you have a positive leading coefficient. So it should be pointing up on both sides. And it does. As you move to the left infinity, it goes up. And as you move to the right infinity, that goes up. So your end behaviors are still going to match. All right, so sketch a graph that matches the following increasing and decreasing end behaviors within this polynomial function. So we're going to look at first if f is increasing when it's less than 0, but then greater than 4. So as it's increasing when less than 0, as it's approaching your 0, it's going up. And then same thing as we go beyond +4, it's going to be increasing. Then between 0 and 4, we know that it is decreasing. So that's why between your 0 and your +4, it is going down. And you know that the graph is above the x-axis greater than 0 here when it's between -2 and 3, and then above 5. And then it dips down to below negative when it is -2 and then between 3 and 5 right here. So you would just have to make sure that it's crossing your x-axis, also known as your zeros or your roots of the equation of this polynomial function. Very similar to the quadratics, and we'll get into that in later sections of this chapter. So looking at a real world scenario. So the estimated number of electric vehicles in the United States can be modeled by the following polynomial function. Whole bunch of fun numbers. I don't need to rattle those off, but your t is going to represent the year, where t equals 1, which is the first year of 2001. So we are going to need to use a graphing calculator to graph the function of the interval between 1 and 10 years after 2001 and describe the behavior of the graph on the interval. Part B, what is the average rate of change in the number of electric vehicles between 2001 and 2010? Part C, do you think the model can be used before 2001 or after 2010? Explain your reasoning. So first, we're going to plug this into our graphing calculator. You can use Desmos, you can use a TI-83, whatever you have handy, but the graph should look something similar to this, where each number on your x-axis is years after 2000, so 2001, 2002, 2003, and so on, and then y is the number of vehicles that are in use in the United States. So from 2001 to 2004, it is increasing. And then around 2005, the growth is slowed down and it starts to level off here up until about 2008, maybe even 2009. And then it starts to increase again in 2009 and 2010. So from 2001 to 04, the number is increased. Around 2005, it starts to slow, and then around 09 and then 10, it starts to pick up again. So the years of 2001 and 2010 are corresponding to your t as t equals 1 and t equals 10. So plugging those into the value of your function, which is that v of t equation that we had starting at the beginning. So when you plug in 1, and then when you plug in 10 separately, you get 58.57 for your 10 being plugged in, 18.58, 4 is repeating when you plug in 1. Then to represent the difference of that change, you have to divide by the change of the numbers that you plug in. Think of this pretty similar to your slope formula. You have rise over run, or y2 minus y1 over x2 minus x1. This is very similar to the same thing, just applications of this vehicle over time function. And the average rate of growth is about 4.443 vehicles per year between the years of 2001 and 2010. All right, so looking at your end behavior, because the degree is odd and the leading coefficient is positive, as it is approaching negative infinity to the left, it's going down, and as it approaches positive infinity to the right, it goes up. So that end behavior will continue to decrease as it's moving left of 2001, and then increase as it's moving to the right of 2001. So eventually you're going to get negative values when you look left of 2000. So it could not be used anytime before the year 2001, because you can't have negative numbers of electric vehicles that are being used. You can, however, have a valid use for it after 2010, because it could have unlimited growth. You could have an infinite number of vehicles, so long as your space allows for it.